everyone. Please pay attention to Carlos and his talk about Linux device model. Please help me welcome here.
Okay, hello everyone. As Dave told you, my name is Carlos, and I am a file system engineer at Red Hat, work mainly on sysfs file system. But today I'm not going to talk about file systems, I'm going to talk about the Linux device model, which is basically how the 2.6 kernel was designed to actually introduce device drivers and organize them inside the kernel. So I have a basic agenda here, so I will just try to introduce some very fundamental concepts about not the device model itself, but about computing. I'm going to talk about what the device model is and why it has been created. And we are going to focus more in the implementation and the sysfs file system during the talk. I also added in the talk a reference guide here. I'm not going to explain how to use the device model API, but I think it might be useful for a future reference when somebody wants to actually see the talk online or something. So let's just start with a very quick introduction about some fundamental concepts. So we have in the device model, we use a lot of these concepts. So the bus concept, which is basically just another device who is used to connect devices with the CPU itself. We have the concept of device, who actually are any kind of hardware attached to your computer, although we can also have virtual device. The driver, which is basically a piece of code who use it to manage the hardware itself, or mainly the piece of code who actually talks with the device, with the device itself. In the device model concept, we have two main important concepts to understand here. The concept of class. In the device model, all the devices are organized in groups based by the device functionality, actually. So, for example, we have the block class. So all the kind of block devices are organized inside the block class. In the class itself, we don't care about how the device is implemented behind the scenes, but about its functionality. So at block class, we know that all devices under the block class will always be a randomly accessed block device. We have the concept of subsystem too, which is a quite difficult concept to explain because it has a lot of meanings inside the kernel layer. But in the device model itself, it's basically a collection of objects of the same type. Like, again, for example, we have the block device subsystem, we have the character device subsystem, and generally speaking, inside the kernel, we have a lot of, almost every system inside the kernel is a subsystem, like the memory management subsystem, the file system subsystem, and so far and so on. And the module, that's basically a piece of kernel code that can be dynamically loaded. So let's start to talk about the device model itself. The device model was one of the main goals for the 2.6 kernel, and it actually is used a lot today. That's why I'm doing the talk, of course. But it has been one of the main goals of the 2.6 kernel, and the goal is basically to provide a standardized way to represent devices inside the kernel. So it's a way we can use to organize all the devices and drivers and modules, or almost everything inside the kernel, in a hierarchical tree. So we can actually walk this tree from the bottom up, like for example, as an analogy, a file system tree. And one of the main uses of this inside the device model is because of power management inside the kernel. So, for example, if you have a USB flash drive attached to a computer, you certainly don't want to turn off the USB hub before you actually turn off the flash drive itself. That's one of the main reasons we use this device tree. And also, it's a very easy way we can connect devices with their drivers and vice versa. So, as we are going to see later, it's very simple using the device model and the sysfs file system to identify which device is connected to which driver and actually which module provides the driver. So as I told you before, in the device model, the devices are categorized by classes. And one of the another goals of the device model was to reduce code duplication. Since we have a very standard API to implement drivers and devices, it helps us a lot reducing code duplication. It also, one of the secondary goals of the device model was to implement a very simple user-to-kernel space communication interface. That is one of the goals of the sysfs file system we are going to talk here too. As I told you, it was one of the main goals of the 2.6 kernel years ago. So, in the implementation is basically where we are going to focus all the talk. And although it's a quite simple design, it's also very complex to understand because we have a lot of pieces working together at the same time. So it's quite difficult to try to to explain this in a structured way. So if you guys have any questions, just interrupt me at any time. So I'll try to explain this better. And I just want to add a disclaimer here that I'm not a device driver. I work with file systems, and we use the device model a bit inside the file systems. So I'll try my best to explain you guys any questions you guys might have, but I don't know everything about it, and I wish, but I don't. So the device model has been designed basically around three main structures, which is the KObject, that we name it usually kernel objects, Keysets, which is basically a collection of KObjects, and KTypes. The name of the structure in the kernel is KObject type, but here I will just say KType, it's easier. So those three abstractions have been created to help the device model implementation, but nowadays it can be used almost everywhere around the kernel. We use this a lot in file system to export information from the file system internals to the user space. And we're going to get to see more details about this later. So the core abstraction of the device model is the kernel object. It's basically a struct of the type KObject, and it provides a few fields inside the struct itself that help us a lot inside the kernel. It provides a name and reference counting. The name of this KObject will, in the future, will be translated in a directory inside the sysfs file system. We are going to talk about sysfs in depth later. It provides a reference counting. So one of the keys of the KObjects are actually to provide a reference counting for devices and drivers. So we, depending on the programmer, of course, you can always be sure you do not remove a device or a module from the kernel with a reference counting that's not 0. Or it provides a parent pointer user to construct the tree of the device model, and it has a KObject type, that it's a KType. We are going to talk more about this later. One important thing about KObject is that the concept of KObject has been created to be used embedded in another high-level structures. So it has almost no use. It has almost no standalone use. So I don't know actually anywhere in the kernel where people use this by itself without embedding it in another structures. So as I told you before, the kernel objects nowadays can be used almost anywhere in the kernel. So the KTypes. The function of KTypes are actually describe the objects who actually embeds another KObject itself. So, for example, we have the character device. The character device have a structure cdev, and the structure cdev has a KObject inside it, and the structure cdev has a kind of KObject type structure describing what exactly a character device is. Each structure must have a KObject type associated with it you cannot have object without a KType associated. It also is used to provide the default behavior of the objects of the same type. So as we are going also to see later, it provides a lot of default attributes to each KObject and each object that actually makes use of it. It also is also used to control to control what happens when a KObject is created or destroyed inside the kernel. Basically, a KObject is created and destroyed when you remove or add some device to the file system, to the kernel itself, or when you remove a module. Almost everything that goes in and comes out from the kernel, a KObject exists for control that. An important thing is that KObjects of this it enables KObjects to actually share the same behavior, so it also reduces the code duplication because we can actually share the same structures between several different objects. So the Keysets, then, it's another concept we should have very clear in our minds here. It's basically a collection of objects of the same type. Sorry, not of the same type itself, but it's basically a collection of KObjects. The Keysets also have its own KObject inside it. So, as I told you before, the KObjects were created to be used embedded in another structures, and the Keysets is a good example of it, although it's also part of the device model itself. The Keysets are also used to control the user event operations about the KObject actually embedded inside it. Usually the U-event operations are mostly used for hot plugging system, but we use this a lot for another stuff, depending. It actually has a lot of usage. So, this is one important thing because KType usually is a collection of several KObjects, but all the KTypes inside all the KObjects inside a Keyset doesn't necessarily need to have the same KType associated with it. We can have a collection of KObjects with different meanings. So this is basically the definition of the structures inside the kernel. I think it's quite important to explain a bit about how those structures are defined inside the kernel. So the KObject, for now here, we have three main fields. One of them is the parent pointer, which is basically used to create the tree of KObjects inside the kernel. The Keyset, who actually is a pointer to the Keyset which this KObject belongs to. A KType that it's a mandatory pointer we need to initialize. And the Keyset structure is very simple actually. It just has a list head of, it's basically a list of all the KObjects inside it. Log for this list, a KObject who actually is the descriptor of the Keyset itself, and it has a function pointer to a lot of U-event operations functions that are the functions used to generate user events. And we have the KType. One of the main important fields of the KType is the release pointer. It's basically a function pointer to a release method. So every time a KObject reaches a zero reference counter, this release function is called from wherever in the kernel it happens. It can be called from everywhere. That's one of the main reasons we have a reference counter inside the KObject. We have a sysfs operations pointer, which actually points to two functions that are used to control the behavior of the attributes of the KObject itself. Attributes are basically translated to files inside the sysfs later, but we are going to talk about it more in depth when we talk about sysfs. So this is an example I was explaining before. We have the structure cdef, that's a structure for creating character device, and all cdef structures have a KObject embedded inside it. And also we have a KType defined here. This KType specifically defines the behavior of dynamic character device. That's one of the easiest character devices we can create inside the kernel. This KType itself just have a release function, so every time a character device reaches a zero reference counter, this function is called. So I'm not sure if it's well organized or if it's a completely mess, but I try to set up here how the kernel organizes the KObjects and the ksets inside the kernel. So basically, we have a kset here, which has the kset list pointing to a lot of KObjects. We have the KObject itself pointing to another KObject. Usually, but it can be different, the KObjects inside the same kset inherits the same attributes from the kset. So they usually points to the same KType inside the kset itself. When the device model has been created, there were another structure that used to be named subsystem, which is basically a structure that embedded only a kset inside it. The concept of subsystem was basically everything that went inside the root directory of the sysfs file system. So nowadays we don't have the subsystem structure anymore. So any kind of kset structure that doesn't have a parent pointer in the KObject and doesn't have a kset associated with it, goes directly to the root of the sysfs file system. Is it clear, guys, for you? I'm not sure if anybody has a question about it. Okay. So, the KeyObject attributes we were talking before, it's basically how the files inside the sysfs file system behaves. Every attribute inside the KObject is translated to a single file inside the sysfs file system. As I showed you guys before, it's pointed by the KType structure. And inside the KType structure, we have the default attributes pointer, which is basically an array of pointers to structures of type attribute. This array is by the implementation, it should be zero terminated, so the kernel knows how it reached the end of the list. The main field, the default attributes field is usually a collection of attributes that are actually embedded inside the KObject when the KObject is created. Usually these attributes are inherited from the parent of that KObject, for example, from the kset where it's embedded in. We can actually create attributes on the fly for each KObject, but I will show you guys later how to do that. Oh, no. So the attributes are handled by the functions pointed by the sysfs operations. So usually, as I told you guys, usually those KObjects, they inherit the attributes from its parent, but it can be created on the fly. One thing that's very important to keep in mind that the functions actually defined in the sysfs operations field, they must know how to handle attributes that are actually created on the fly. So when you create a KObject, you have a set of default attributes, but any other attribute you created on the fly for some reason, because you don't know if it would actually be useless if you couldn't actually create non-default attributes for different devices inside the kernel. The sysfs operation functions, they must know already how to handle these attributes. So if you are planning to create a non-default attribute, these attributes should be already implemented in the functions. So this is basically the definition of those structures. We have the KType here again with the default attributes field and the sysfs operations field. Each attribute is basically a name and an access mode. This access mode is actually the mode which the files inside the sysfs file system will be using. And the sysfs operations structure, it has only two function pointers. The show, which is used when you are reading a file inside the sysfs, and the store, which are actually when you are writing a file inside the sysfs. As I told you before, if you are planning to create non-default attributes, those functions must already know how to handle these attributes. And it's up to the developer to actually choose how this show and store functions will actually recognize different attributes. So usually, I think in 80% of the case, you only see a huge switch definition inside these functions, usually using the name of the attribute to understand which attribute is being called or written to. So about the kernel event layer is the kernel notification system to user space. So everything we want inside the kernel to notify user space, we use the kernel event layer now. It's mainly used for hot plugging, defined in the Keyset event ops. I will show you guys later how it works better. When you are actually sending an event to user space, you must use one of the already predefined actions. It has a netlink socket that actually connects the kernel space to user space. And one important thing is that for each event, only a single action should be involved. So the Keyset event ops structure, it actually provides 3 function pointers for us. One of them is the filter pointer, who actually is used to decide if an event for that KObject should be created or not. So if you're creating or destroying a KObject, you might not want, for example, to notify user space about it. So you can use this filter function to actually filter what actions should be passed to user space or not. One example where we use this a lot is in the block devices. When, for example, we partition a disk, we really want to notify user space about it. So we actually use these functions to notify user space about partition changes inside the block device. But for example, when we change request queues for I/O operations, users used to not care about it. So we actually use the filter function to avoid request queue changes to be sent to user space. We have a name function who actually provide the name of the subsystem generating that event. So if you guys have any experience with the udev tool, you should probably have seen they have a subsys field in the udev request. So this is where the subsystem field from the udev takes the information from. And we have the uEvent function pointer too, which is basically the main function pointer we use to notify user space. It's basically a function we use to provide user space with a lot of environment variables regarding the action that's being involved. For example, when we plug a USB device, it can provide to user space variables like the version and serial number and vendor ID and things like that. And all of the actions about events inside the kernel are defining a KObject action enumeration type. So the kernel developers and the device model maintainers, they have no objection in adding actually another actions inside this field, but you should have a very good reason to add another one. So every time we want to send an event to user space, the event should be one of these actions here. And also provided with these information from the subsystem and the environment variables you want to pass to user space. So the sysfs file system, it has been created basically as a helper to get information about the device model itself. So users can actually have a user view of the organization inside the device model. But nowadays it's also used for almost any kind of user communication we want to pass from the kernel to user space or vice versa. So it basically is a virtual memory file system. It doesn't have a block device attached with it. It exports to user space a friendly organization of the KeyObjects inside the kernel. Each sysfs corresponds to a single KeyObject. So each directory inside the sysfs corresponds to a single KeyObject. it's not mandatory actually you export a KObject to the user space. So you can have a lot of KObjects inside the kernel that doesn't show up in user space or sysfs. But each attribute from the KObject, it must have a file associated with it in the sysfs. The kernel actually creates this automatically, so there's no way you create an attribute without having a file inside the sysfs. And as I told you guys, it's one of the main ways we have from users to kernel space communication nowadays. This is I try to do a sketch from the sysfs file system inside my laptop, so to try to explain better how it's organized. So we have the sysfs itself, and here we have the root of the sysfs file system with all subsystems inside it, almost all of them at least. So we have fs subsystem where it contains almost everything related to the file systems. Every kind of KObject used inside the file systems are represented inside this directory. We have one of the main important fields for us here is the device directory, where it contains basically the organization of the whole hardware of the computer inside it. So this is a view of my laptop. So here I have the device directory. This one here represents my PCI bus, so I have one directory and one KObject representing my PCI device. I have a PCI slot here connected to an ATA controller. So this ATA controller has all the SCSS layers, host, target stuff. And down to the stack we have finally the SDA device, which is a block device. So the block devices are all collected inside the block directory here. They are usually symbolic link pointed to this more complex structure here. And one of the more interesting things about sysfs is that it's very easy to understand which module are being used by a driver and which each device actually use a specific driver. So for example, here I have inside my PCI slot descriptor here, I have a symbolic link named driver that points to my A8CI driver. That's actually the driver who controls my PCI, my ATA PCI interface. And inside this directory here, I have a module symbolic link that points to the module who actually implements this driver. So this is another view of my computer too, but I try to explain here what happens when you connect an external USB disk. Actually, it was a suggestion of a friend of mine. So we can see here that those directories here are basically the same. I have my PCI interface here, my PCI bus here, and I have a different PCI slot here connected to a USB hub. And this USB hub, I have a specific port of this USB hub is pointing to a driver that actually belongs to the USB storage driver, who actually handles all the USB storage device. And after here, I also have again the SCSI interface. So we have the host and target. The targets here are different. But here I added another example that showing the driver controlling actually this directory here, this device, is actually the SD driver or the SCSS driver. And I also have the SDB device here pointed by a symbolic link inside the block device. So I added a reference guide here, as I told you guys. Let me see. So I added this reference guide here. So if in case somebody wants to play with it or work on device model itself, can have I try to make it simple. So a few important considerations here are most of the time, device drivers don't use to actually work directly with KObjects and Keyset and things like that. Almost all subsystems nowadays, they actually provide their own sub APIs to manage the device model behind the scenes. So I added here a few functions about how to handle KObject itself. Here are a few important things about KObjects. A KObject must have a name and a parent pointer, and it actually, the KType and Keyset must be initialized, and also the KObject should be zeroed when it has been created. So usually when you see a KObject being created, you always see a memset zeroing all the fields inside the KObject. So a few functions to handle the Keyset, in case you guys are interested in see it later. So we have a few things I would like to talk about here. So as I told you guys before, you actually can create attributes for specific KObjects on the fly. You don't need to actually rely only on the default attributes. So the sysfs create file and remove file functions are used to achieve this behavior. And actually the symbolic links are not mandatory too. So we have a lot of drivers inside the kernel without symbolic links pointed to anywhere. So nowadays if you are writing some driver or some device model inside the kernel and you don't actually provide the symbolic links, probably your patch will be rejected. But we still have a lot of patch missing symbolic links and good references for that. So I'm not sure if I have time yet, but I was planning to provide some examples here. Oh. So let me try to finish the slides and I'll try to show about a few examples later. As I told you guys, the device model nowadays, actually the KObjects, Ksets, KTypes, they were created as an abstraction to provide support to the device model itself, but nowadays it's used in almost anywhere inside the kernel. So in file systems we are a heavily user of it. For example, the sysfs file system where I have most expertise with, we use it to export a lot of statistics from file systems, from the file systems itself, and in journal information from the file systems. We used to have this information in the proc file system, but recently we moved it to the sysfs file system. So, if you guys want to know more about it, there are a few interesting places you guys can use. One of them is a blog from Greg Hartman. I don't know how to pronounce his last name, but Greg was actually the designer of the device model, so he has a very nice blog post about how to create sysfs files correctly. Two books that actually are were very useful while I was actually planning this talk and studying the subject itself. The device driver, that's very known book, and the kernel development from Robert Love too. The kernel code has a lot of documentation about it, and the source code itself. The source code is quite complex to understand if you don't have a 2,000 feet idea about how it works, but I think it's still the main source of information. There's a project about related with the device model itself that's named Linux Driver Project. I'm not sure if you guys know about this project, but it's a project with a lot of device drivers developers. They actually help companies who actually want to have a hardware supported on Linux, but they don't have time or they don't want to spend time in actually developing drivers for these hardwares. So it's basically a group of kernel hackers. I think that they are sponsored by Linux Foundation. They actually help companies to provide drivers for their hardwares in Linux, and they are actually willing to sign non-disclosure agreement regarding confidentiality about drivers, about hardware and hardware projects, etc. So for people who actually want to have hardware devices supported on Linux but don't have time to work on it, it's a good place to take a look on. And also they accept another volunteer, so if anybody wants to work on device drivers, it's a good place to start. If somebody wants to ask me contact some questions, I just added my email here, and I will provide this talk available on my Red Hat page, and I think DevConf will also upload it somewhere. And I'm always on IRC, so if somebody wants to ping me anytime, just feel free to ping me anytime. But again, I'm not a device driver, so I'm not a device driver developer, so I'm not sure if I will be able to answer all questions. But if somebody has any questions about file system, just talk to me. So thanks a lot. I'm not sure if anybody has any question. No. Good.
In fact, Carlos has an opportunity to record 3 of you for a question with a star.
Good.
Do you have any questions?
Did I explain so well that time? Okay. Thanks, guys. Thanks.